Welcome everyone. So we're back to our investigation of forces, and particularly today, and I'm very excited, we're going to be looking at friction. Friction is so important. Up until now in your science, we've ignored friction because it makes our calculations a little more difficult, but actually we all know friction exists, okay? So we're going to look at that today. So where are we going? Well, we need to first understand what is friction. What causes friction? Where does it come from? Why does it exist? Because it's not like we want friction, but it's there. So we have to talk about that. Then we're also going to talk about, can we change the amount of friction that an object experiences? How do we change that? Why do we sometimes put oil in motor cars to oil the parts? Why do we sometimes put oil in doorknobs or things like that? What is the point of that? Why does it make it go quicker or slower, or why does it make it easier to turn? Those are all things where we're changing friction. When you buy new shoes and then they're slippery, this is bad. How can we change that? Why do we need friction? All of those things are important, okay? So, when we look at our mind map, which you've seen a few times, we're now looking at friction. So what are our key words for today? Friction, what is it? We'll be able to explain it. But then there's two types of friction. We get static friction and we get kinetic friction. Those are very important. They're both frictions, but they act on objects in different situations. And then we get the coefficient of friction. That value is very important, and we're going to use it lots. Okay? So, looking at friction, let's break friction down a little bit. And the first thing we're going to look at is what causes friction. All right? Now, friction, you know, happens when surfaces rub on each other. Now, even the smoothest surface has microscopic little bumps in it. And that's really important. So I've got a little bit of an animation to show you. So here we go. Now, this is a chemistry book and a physics book. Great. And as you can see, there's the particles. So this is the physics book in the green. That's the chemistry book in the blue. Now, those particles are the solids. Now, you know from chemistry, those particles are constantly moving, so they're vibrating. But even with the chemistry book, there's little bumps. Now, you won't be able to feel that with your fingers, because you can't. They're microscopic, so it feels smooth. But when I move the chemistry book, so when I move them over each other, they have to rub past each other. That's the friction. So when these are now rubbing past each other, that causes friction. And can you see that they're starting to move more? They're actually heating up. Friction always causes heat. So you can see that. But it doesn't matter how smooth it feels, that's there. Sometimes we can make it very, very smooth, so it's like the friction doesn't exist. And we have to fill in those little gaps. But most of the time we can't. And you see with the temperature going up, you'll know when you rub your hands in winter, you do that because the friction causes heat, nice and hot, okay? So friction is caused by two surfaces rubbing on each other, and the fact that you've got those little microscopic bumps because of the atoms that have to get over each other. It's like climbing little hills every single time. And obviously, the faster we move it, you can see higher the temperature, okay? When they're not in contact, there's no friction, okay? But it's those microscopic changes. So, where am I going? There we go. Then we get types of friction. We're not going to spend the cause, that's all you need to know. Types of friction is different. So with our types of friction, we get static friction. Now, static friction is when objects aren't moving. Static means not moving, okay? Like electrostatics, static electricity, charges, stationary. So when objects aren't moving, there's static friction, but there isn't always static friction. We're going to talk about where there is and where there isn't. As soon as an object starts moving, we get kinetic. As soon as an object moves, there's kinetic friction. We can't get away from that. we can reduce it, we can make it smaller, okay? If we can make those little ridges smooth as possible, we can reduce the amount of static friction, but we can't get rid of it. Static friction, stationary, may or may not be there. Depends on the situation. Kinetic friction, always there when an object moves. Sometimes we choose to ignore friction to make our calculations easier, but that's all. It's not because it's not there, it just makes it easier. Okay, that's the only reason. So, we're going to stop there for now. I know it was short, but in the next section, we're going to discuss static friction and kinetic friction in lots of detail. So get your head ready, okay, and I'll see you in a couple of minutes. Okay, so welcome back. Now we're going to investigate friction. We're going to do lots of detail, all right? So what we're going to do is we're going to talk about what happens when we can't ignore friction. When there is friction, how does an object move? What happens to the friction? Okay, so we're going to show you an animation, so watch. So here we have our little man, which we've seen previously. But now I have a situation where I've got friction, okay? I can make it a lot of friction or a little bit of friction. We're not going to worry about that. The friction depends on the objects, okay? So we're not going to be too stressed. Now what I want you to see is I'm also going to put the forces are going to show, all right? So here we have our little man, and now, he's applying a force. Now if you look carefully at what's happening, it's not moving. So what this means is he hasn't overcome friction. When there's no force, so he doesn't apply any force, so I'm going to make that 0. Let's just go, whoopsie, wrong way. Doesn't matter. There's no force. There's no static friction right now. This box is not experiencing friction. We're not trying to move it. When I put the force on, you can see, if you look carefully, that as the applied force gets bigger, so as he pushes it, friction pushes back and also increases. So let's put some values in there. The applied force is 25, friction is 25. This is still static. The box isn't moving. As I increase the applied force, if you look carefully, applied force is now 47, friction is also 47. So friction got bigger. It matched the applied force. This is what we mean when we talk about when we move an object that we have to overcome friction. We have to overcome the static friction. Static friction gets to a maximum. So now watch. We keep going and we apply, and it's getting bigger and bigger. So it's quite a heavy box, which is why it's taking so long. So we get here. Now watch. I know it's not moving. Speed 0. Keep going, and we've now got over 100. We get in there, 112, 113, 100, there we go. And eventually, did you see what just happened? Boxes started to move. Look at that force. Friction is now 94. So when I got to about 125, that's where it switched. Okay, now me going down, so if I go here, so now I'm going to change this force. Now it's going to slow down because friction is now bigger than the applied force. So he's actually going to slow down. But that 94 didn't change. It's moving. Because it's moving, we now have kinetic friction. But kinetic friction doesn't match the applied force. So now we've got to look at something different, all right? So let's just reset this, okay? And we know that the original force here, no, that's too far. Let's reset again. Let's put the speed up there, and we want the values. So we knew we got to about here before, oh, look, it doesn't want to play with me. Okay, fine, we'll do this then. We'll do it this way, it doesn't like me using that. So we knew that we got quite far, okay? So remember, at 94, when it was moving, it's not moving. Static friction, okay? Static friction is hard to overcome. When an object is stationary, it's very difficult to start it moving. So we actually have to apply a lot of force. And here, it's round about here that it almost changed. So we've got to 117, 118, 119, 20, 23, 24, 25. At 126, it starts moving. That changed to 94. Once we start an object moving, kinetic friction drops. It's just the concept of once it starts, it's easier to move. It's always easier to keep something moving than to start it moving. Okay? So, static friction, when an object is stationary, okay? That static friction is 0 if we're not pushing, so if it's just standing. Soon as we start pushing it, the static friction has to match the applied force. So we're pushing, 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 so they match, the object doesn't move. Then we get to that moment where we get just over the maximum, so there's a maximum for static. Once we get past that, it becomes kinetic friction, and that kinetic friction is constant, okay? Now, this was a box with a mass, let's just have a look here, of 50 kilograms. What we're going to do is we're going to change it for, no, I don't want, there we go. We're going to put the fridge, which is 200 kilograms, okay? We're going to do the same thing, okay? Now I'm going to apply force to it. And again, force, static friction, it gets bigger and bigger. Let's just put the values in because it makes it easier. Whoops. So here we go. Oh boy. We expect to have to push a lot harder. We expect that there's going to be more friction because it's 200 kilograms. It's big, big mass. Very difficult to get it to move. So we keep going. And it's going to be a long time before it gets to move. And it goes and it goes and it goes and it goes. Oh, look. Eventually, this is a very strong man. Okay. Oh, yes, he's pushing hard. I don't know if he... yes, no, he's going. He's going. No, yes. There we go. Almost. We should be almost there. Oof. He might never move. So you know what we're going to do? We're going to cheat a little bit. We're going to get rid of some of the friction. There we go. Now we can get it to move. Okay, there was way too much friction. You would never actually eventually get it to move. Now if I take that force away, so now I take all those forces to 0. The object still moves. Static friction doesn't disappear, but eventually that static friction will cause it to stop. Now it's stopped. That static friction is gone. Sorry, the kinetic friction is gone. Now it's static friction, and it's 0 because there's no force acting on it. Okay, movement, kinetic friction. No movement, static friction. The mass of the object was very important. Very, very important. Okay, so let's go back here. So we've done that. When we look at static friction, this is the definition. Definitions are very, very important. It's the force that opposes the tendency of motion. Please be careful here. It's very easy for you to go, it's the force that opposes the applied force. It doesn't have to oppose the applied force. Okay? It can be in the same direction as the applied force. What it opposes is the way the object wants to move. It's always in the opposite direction to motion. Now, with static friction, It's the tendency of motion, so it's the way we want it to move, because it's not moving, of a stationary object relative to a surface. We have to have a surface, okay? Now, how much that static friction is depends on the two surfaces. That's very important. Then, the maximum, and this is a new symbol for you, where we've got, and we usually write this F as like an italics F. It's a little bit of a curly F. It's not a straight F. Though, if you did write it as a normal F like that, that's fine. We just normally write it to a slant. F maximum, F for friction, little f, S for static, max for maximum, okay? Is the static friction just before an object starts moving. So when they describe this in questions, they'll say to you that the force applied to an object is, say, 100 newtons just as it starts moving. That's the maximum static friction. That's an important value for us. The other values, as it gets bigger and bigger and bigger, not that important. Maximum static friction is important for us, okay, because that's the friction we have to overcome. Then, kinetic friction is the force that opposes the motion, not tendency to move now, but the actual motion of an object moving relative to a surface. So static, stationary, kinetic, moving, okay? Now that's a constant. Kinetic friction is always smaller than the maximum friction. There will be no situation where it's the other way around. So if you're looking at calculations and you work out the kinetic friction to be bigger than the maximum static friction, you've made a mistake, okay? It doesn't always have to be a big difference, like we saw in the animation, it was about 30 newtons. Doesn't have to be big, it can be small, but it must be a difference, okay? They will never be the same. When we look at friction as a force, there's a couple of things we need to take into consideration. Number one, it is independent of the size or the area of the object. So if we look at the fridge again, whether I had the fridge standing upright on its side, it wouldn't make a difference. So the area, so whether I'm looking at my hand against my hand, let me put my pen down, whether my hands go this way around on each other or this way on each other, they'll have the same amount of frictional force, because it's not about this area, it's about the surfaces, it's about the type of surface, okay? That's the first thing. Secondly, it is dependent on the mass. It is absolutely. The mass results in a gravitational force. So basically what we're saying is how much force does the object exert on the ground, okay? So the heavier it is, the bigger the force it exerts on the ground. The closer the two surfaces can become, and the closer they become, the more friction they'll experience, okay? And it's the same when you rub your hands. If you only do it lightly, they don't get as hot. When it's really cold, you push them really hard together, because then they get nice and hot, okay? So, it is dependent on the type of surfaces. Whether we have wood on metal, wood on wood, wood on plastic, metal on plastic, whatever, the two surfaces are important. And this is not, we can't affect that. So we can't go, this plastic for this situation, if I have wood on plastic, one time it's going to be easy, next time it's not going to be easy. No, wood on plastic has a certain friction. It is what it is, okay? We can affect the amount of friction by the way we apply the forces to it, but we can't change how the two surfaces relate to each other because of their microscopic properties, okay? So it does depend on the surface. If we change the surface that an object is moving on, we change the friction that it experiences, okay? So, very important, it always acts in the opposite direction to the motion. And I see this often, particularly when we've got objects on slopes, okay? Because we want the friction to always go up the slope somehow, we tend to forget that the friction can also act down the slope. If I'm pulling an object up the slope and it's moving up, friction has to act down. If I'm letting the object slide down the slope, friction has to act up. Friction opposes. Friction doesn't go in the same direction. Friction isn't helpful for us in this situation, okay? Friction takes away. It's bad, okay? Friction, now here we get into some important terms, is directly proportional to the normal force. So what that means is, remember, the normal force is the force that pushes up on the surface when the object's on it. Directly proportional means that if I double the normal force, I double friction. If I halve the normal force, I halve friction. They do the same amount. So how do I change friction? I have to change the normal force. How do I do that? Make an object go force at an angle, okay? But it's directly proportional to the normal. That's very important. If we change, and they'll ask you this, if we change the way the forces act on a body, which then changes the normal force, we change friction. There's no exception to that. And it changes both static and kinetic. Okay, so it's not just the one, it's both. Very important. Now, when I put it as a mathematical relationship, this is not an equation. F max is directly proportional. Remember that little fishy sign? Means directly proportional to the normal force. This is well and good, but we need it as an equation, okay? I can't do calculations from this. This doesn't help me. I can't work out F max. I need to have a relationship. So, kinetic friction is also directly proportional to Fn. These are the same. From here, I want to get to a calculation. I want to get somewhere with this. So, that gets us to the coefficient. Please, you need to know what this symbol means. The coefficient of static friction, mu s, and it's a u, when you write it, it's always difficult when you see it typed, but when it's written, it's like a u that's backwards with its tail on the left-hand side. It's a Greek letter, okay? Mu s is the ratio of S max to Fn. Ratio division, so I'm dividing newtons by newtons, so it doesn't have a unit, and it's a constant. That gets rid of the proportionality, okay? For two surfaces, every pair of surfaces has a specific constant. That changes. You don't need to know these constants. It's not like I'm going to give you a list in a big long table. I can't tell you them. What will happen is either you'll have to work it out with the information given, or they're going to give it to you and you can use it in a calculation, okay? But it's a constant, no units. It's one of the few things you have that have no units. That gives us this equation. You will be given that. That's on your information sheet. Often I sort of joke it a bit. I don't like using the fraction. I just don't. So I often will write it this way around. Okay? Now this constant, right, depends on how this works. They're usually smaller than 0. Okay? They can be big, not smaller than 0, smaller than 1. Really, 0, they can't be negative. They can be bigger than 1. That means there's lots and lots and lots of friction. Those surfaces aren't great. Okay, it means that it's very difficult to use. We don't use them in science because it means we can't get things to move. When we look at kinetic friction, it's also a ratio. Kinetic friction to Fn. But now, it's mu with the K. So the coefficient symbol is the mu. Whether I'm working with static or kinetic friction is the subscript. So you have to put that in there because they're two different types of frictions, okay? That leads us to this equation where my coefficient is the ratio kinetic friction to normal force. I don't like fractions. I don't like friction really either, but that's besides the point. That's how I will often use it like that. Also, how we use it depends on what they're asking you. Because sometimes they're going to ask for friction, sometimes they're going to ask for the coefficient. It's implied in your questions that you can work out the normal force. So that's not something they're necessarily going to say, work out the normal force first. It's going to be implied that you need it, okay? So, lots of things for you to think about. We still have a little bit more theory because we need to put this on a graph. We know how important graphs are, but we're going to stop there for now and we'll carry on after our break. Welcome back. Last part. Let's get into the last part of this, okay? So remember, we're still doing friction. Now, we need to look at the graph. Graphing is very important in science. It helps us explain relationships. So if I took the animation we did earlier and we could plot a graph of what we saw, this is what it would look like. So we get a graph that looks like this. We have a graph of frictional force on a horizontally applied force, so like the man pushing the box, for an object that starts to move on a rough surface. So there's friction, okay? This is what happens. Friction force is my dependent variable. It was what we were measuring. Applied force was the independent. It's what we changed. So this first part, this purple line that you can see that goes up at an angle, that is what happens with static. Remember, the static frictional force got bigger and bigger and bigger and bigger, okay? So over here, we have our static friction, which is equal to the applied force, but can be smaller than the maximum friction or can be equal to the maximum friction. Okay, that's what this little part says here. Remember, this equation is for working out maximum static friction. So here, this whole section here, the object's at rest. It's not moving. Then we get to this point, and there's an immediate drop. You saw that. There's no time frame. It's immediate. It drops. That's maximum. Now we get kinetic friction, which is a constant. So at that point, it starts moving. And this is always difficult because when we describe it in questions, I often get asked, but ma'am, it's already moving. Why is it static friction? When the question describes it as the force applied as it starts to move, they're referring to the maximum static friction. It feels weird because there's movement involved. The key word is starts to move. That's the key part there, okay? This line here, that horizontal line, that's the kinetic friction. That is constant. That will not change. Doesn't matter what I do with the applied force. If it's moving, and you saw that in the animation, if I take the applied force away, that friction will stop it from moving. It'll eventually stop. Once it stops, no friction. Friction's gone to static, no applied force, it's zero. Okay? This is an important graph. Very, very, very important graph for you to know. Okay? Now, let's do a question, because that always makes it make a bit more sense. A toy box and its contents with a mass of 20 kilograms. This is a very big toy box. Okay, let's just go. It's 20 kilograms. stands on a horizontal floor, so it's flat. The coefficient of static friction between the floor and the toolbox is 0.4. So first of all, keywords, stands. In other words, it's not moving, static friction. Coefficient of static friction, 0.4. They are giving me mu s. When you read a question, underline important things. See what the important words are. That helps you put it into context, okay? Then they say, calculate the maximum horizontal force that a child must exert to just start the toy box moving. Just start moving, maximum static friction, okay? So they're saying to you, what is, that should be an S, not a, okay? So they're going, I need to know maximum static friction because as it just starts to move, my applied force is equal to my maximum static friction. We know that that's going to be mu s Fn. Hopefully you're now going, but we don't know Fn. Of course we do. Remember, toy box, okay, gravity acts down. What resists gravity? The normal force. Because that's vertically like this and it's moving horizontally, the normal force is equal to the gravitational force. And we know that we can calculate gravity by going mg. So let's think about this. I know mu s, they told me it was 0.4. Okay? I know Fn because it's going to be equal to Fg. So I'm actually going to put that in straight away. My mass was 20, and we remember because we've done this lots, G is 9.8. Okay? Now we use our calculators. Okay, so we take our calculators out. Let's just put it so we can see. Let's put it on the side. So here, we've got 0.4 times by 20 times by 9.8. No fractions, okay? So we're going to change it into a decimal, 78.94. Oh, wait. Let me just 78.4. I don't know where I got the 9 from. Let's just go with it. Now, what we've calculated is static friction. The question wanted minimum horizontal force. So that's the applied force. So now we have to answer the question. That means that the applied force from the boy, if applied, is going to be 78.4 newtons. In the past, I've told you vectors are forces are a vector. I cannot put a direction in terms of left, right, up, down. I didn't tell you which way the boy or the child was pushing the toy box. What I can tell you, though, is this needs to go in the forward direction. That's as good as it can get for direction here. Because I don't have a diagram, if I had a diagram, I could relate it to a diagram. If they had said pushing it west or south or east or whatever, then I could do that, but they didn't. Forward's fine. Forward's a direction. Okay? We all good? All right. Now, a model car and some blocks together have a mass of 2.5 kilograms, are taken out of the toy box by the child. He's having some playtime. That's good. Calculate the new force needed to move the toy box. That should say toy box, not toolbox. Now, when we look at this, first of all, we've taken stuff out of the toy box. Mass is smaller. That means a smaller force. But the first thing we need to know is what is the new mass? So my original mass was 20 kilograms. We've now taken out 2.5. So that gives me 17.5 kilograms. That is the only thing that has changed in this question. What they're wanting you to see is that the applied force is actually going to be smaller. So we're still going to do maximum friction mu s didn't change. It's still the toy box on the same surface. So it's still 0.4. But now my mass isn't 20, it's 17.5. G is still 9.8. Okay? We take our calculators out because we can't do this in our head, so we're going to get rid of what's there. 0.4 times 17.5 times 9.8. Oh, no. There we go. 68.6. It's smaller. So, 68.6 newtons. We expected it to be smaller because the mass was smaller. Mass being smaller made the normal force smaller, and they're directly proportional. We need to answer the question. .6 newtons forward. Smaller mass, smaller friction. All right. So, gave myself lots of space. Here's our summary of what we've done. Okay. Friction opposes motion. Please, that's the important thing. It opposes motion, not applied force. Static friction is the tendency to move. This word's quite important because friction opposes motion, which I've just said to you, but with a static object, it's not moving yet. So it's opposing the way it wants to move, okay? Static, stationary object. Kinetic friction opposes motion of a moving object. Moving, kinetic, moving, like kinetic energy. It's got to be moving, okay? Kinetic friction, always smaller than maximum static. Always, always, always. Friction, this is the big one out of all the properties we did, is dependent on the normal force. That's the big thing. That determines friction for us. We can't change the amount of friction between the coefficient because of the type of surfaces, but we absolutely can affect the normal force. The coefficient of friction, now this is a definition. This is the weird one when it comes to your exams because they may say to you, what is the coefficient of friction general? Or they might say kinetic friction or static friction. You've just then got to add in static or kinetic in the definition. So the coefficient of friction, which is the symbol mu, and we either put an S or a K, is the ratio of the friction and the normal force. Ratio means division. Coefficient, no units. Okay, very important. There's mu S with maximum static friction, mu K, kinetic friction in the normal. Okay, just as an aside, you may see these equations with an N instead of Fn. Okay, they're given to you on your information sheet. That's always nice. We like it when they give us equations. And that brings us to the end of today. So we've finished friction. We've still got to look at force and motion, and we're still going to look at Newton's second law, but that's coming up in lessons to come. But we're done for today.